Hello everyone, this is Chunqi Yuan from University of Science and Technology of China, and I'm very pleased to be here to make a talk. Today I will report about an improved closed-loop Herriott-cavity-assisted isotope comagnetometer. And here is a plot of the isotope nuclear magnetic resonance comagnetometer. We use a pump B to polarize the rubidium atoms. And the rubidium atoms will be polarized, and the zinc atoms will be polarized by spin exchange collisions with the rubidium atoms. And the rubidium atoms can also be used as an in situ magnetometer to detect the zinc signals. And the figure on the right side shows the open loop response of the zinc atoms with a driving field in the y direction. And the red line is the amplitude response and the blue line is the phase response. It can be seen from the figure when the bias field B0 in the z direction changes, the amplitude, the driving field frequency will be off resonance, and the blue line, the phase will have a linear response. And we can reach a closed loop operation by sending the phase results to a phase locked loop, where the phase beta is set to 0, and we use the feedback signal to control the frequency of the driving field. In this way, the driving field frequency will always be on resonance. And here on the and here on the we simultaneously measure the frequency of the zinc isotopes and the precision frequency of the zinc atoms, and the rotation along the bias field can be extracted as this. And you can see from this expression that the rotation measurement won't be influenced by the fluctuation of the main magnetic field B0. One problem is that the performance of the nuclear magnetic resonance gyroscope is limited by the sensitivity of the rubidium magnetometer. So nowadays, there are mainly two ways to improve the sensitivity of the rubidium magnetometer. One is active. Parametric modulation is one of the most commonly used active methods. And however, the magnitude of the modulated field BC is comparable to the magnitude of the main magnetic field B0, which can potentially affect the system stability. So here we use a passive method where a multipass cavity is used as shown here to increase the signal to noise ratio of the rubidium magnetometer. And here is the sensor setup. The main magnetic field is 160 milligauss in the z direction, and the zinc atoms are pumped and probed by the rubidium atoms and are continuously driving by the oscillating field in the y direction. And the size of the sensor is shown here. We finished the first version of our nuclear magnetic resonance gyroscope 3 years ago, and it had demonstrated an angle random walk of 0.06 degree per square hour, and a bias stability of roughly 0.2 degree per hour at 2000 seconds. The cell we used at the time is shown here, and the component of the cell is shown here. So from then on, we made several improvements to our system. The first improvement is that we separate the cell and our Herriott or the cavity into two independent parts. And here is the construction of our cell. This helps to provide a cleaner environment for the nuclear spin atoms, zinc atoms, and with the help of better cancellation of the gradient field, the relaxation time of the xenon atoms and the signal-to-noise ratio of the system are improved. So first, we measure the relaxation time of the xenon atoms using the decay signals with our pumping net on. And we can get T2 of xenon 129 is 10.7 seconds, and T2 of xenon 131 is 70 seconds. And the sensitivity of the rubidium magnetometer is also improved, and which can reach a sensitivity of around 300 Tesla per square hertz, as shown in the picture. So the second improvement is that we operate our closed-loop system in a special phase-locking point where the rotation measurement results are independent of the environment temperature. So ideally, the xenon isotopes feel the same effective fields from the polarized rubidium atoms. And therefore, from the equation, from the rotation expression shown here, the temperature dependence of omega-1 and omega-2 are cancelled. But in reality, there are some additional effects that break this relationship. The first one is that different xenon isotopes will experience different effective magnetic field from the polarized rubidium atoms due to a tiny difference of their collision properties. And this effect will bring in additional terms in rotation, which is omega-1. And the second is that the unresolved xenon 131 quadrupole splitting will also introduce an additional new terms besides the expression of the ideal condition, and which is omega-2. You can see from the picture the xenon 131 quadrupole splitting has a large temperature dependence, so which is true for omega-2. The third one is that we usually set the closed loop phase locking point beta to be 0, but sometimes it may not necessarily to be at 0. This will also introduce an additional terms in the rotation measurements. The beta and omega-3 can be expressed as this. Omega-0 is the precision frequency of the xenon atoms when beta is 0, and omega-d is the driving field frequency. Gamma-2 is the relaxation time of the xenon atoms, which is temperature dependent. So you can see from the expression of omega-3 that the temperature dependence of omega-3 relies on gamma-2. Therefore, omega-3 is also temperature dependent. So we have three temperature dependent items in our rotation. And the temperature of the whole closed loop systems can be expressed like this. We can make the temperature dependence of it to be 0 by tuning the phase locking point beta. Here is the experiment results of the rotation dependence on temperature at a different beta. And you can see that there exists from blue line, there exists a beta to make the temperature dependence of the whole system to be 0. So with the improvements above, we collect 30,000 data, and our updated nuclear magnetic resonance gyroscope has demonstrated an angle random walk of 0.015 degree per square hour and a bias stability of 0.04 degree per hour at 2000 seconds. So we analyzed the experimental limitations on the performance of the nuclear magnetic resonance gyroscope to achieve 0.05 degree per hour stability at 1000 seconds. We analyzed the factors including stability of temperature, stability of pumping net frequency and power, and the probe light frequency and power. So we finally found the pumping net power is currently the factor limiting the performance of the nuclear magnetic resonance gyroscope. So special cares have been taken to maintain the stability of the pumping net power. And here is the pumping net part, and we especially measure the temperature dependence of the elements inside. And we find from the figure these three elements, PBS, optical attenuator, and PD, and its correlated circuits have shown larger temperature dependence than half-wave plate. And we control these three elements temperature at 31 degrees Celsius. And the system become more stable. So overall, we have improved the nuclear magnetic resonance gyroscope by separating the cell and Herriott cavity, and by operating the closed loop system at a special phase locking point. And we also analyzed the limiting factors on the performance of this system and found the pumping net power is the limiting factor. And in the future, we will use the Earth rotation to calibrate our nuclear magnetic resonance gyroscope. And that's all. Thank you.
Thank you very much for the talk. Questions?
You may mention this, but what are the length scales of the cavity and paper cell?
The size of the cavity arm. It's about 21 score 16, and the height is about 12
millimeters. Is that right?
Millimeters.
Yeah. Okay. Other questions?
Was that the T2 time?
Yeah, go down. That's why, yeah. So why is T2, or is this T1 or T2?
T2.
So why is 131 better than
Because
129?
Because we separate the cavity outside of the cell, and the collisions between the xenon atoms and the mirrors are reduced, and it provides a better environment for the xenon atoms. So it reduced the collision areas between the two. So our T2 becomes larger.
And why is there a difference between the two isotopes? Like, that's your question, right?
Because why is the difference between these two? Because their spin exchange rate is different. Gamma, the zero magnetic ratio for gamma for xenon 131 is 3 times larger than about 3 times larger than 0129. So the T2 is different.
My question was actually like the difference in sensitivity is solely because of the difference in T2 time. So your 121 performance was better than your 129 performance. Is that only because the T2 time is different, or is it something else?
Oh, we also cancellate the gradient field in the z direction with 1 order and 2 order compensation to make the field in the z direction more uniform. Okay.
Thank you.
Any other questions? There's one.
Can you talk about how to measure the Earth's rotation?
We haven't made the Earth's rotation, so we will currently we will put it on a turntable, and we will and put it on a turntable, and we will maybe make it yes, but the system is closed loop, and when it rotates, it will contain the Earth's rotation, and we mainly want to calibrate the Earth's rotation to prove that the bias stability of 0.04 degree power is true. Yeah, it's usually used to nuclear magnetic resonance oscilloscope is used to test the rotation velocity of the carriers. So.
Okay, let's thank the speaker again. Thank you very much.